Example 3, we're doing the same thing. We're still finding the intervals where we're concave up and down and any inflection points. So we've already found the first and second derivative for this function. Now let's try to find the partition numbers for the second derivative. So remember, those partition numbers, f double prime of x is any place where it's equal to 0, and f double prime of x any place where it is undefined. This is all part of, recall, step number 1. So any place where I'm undefined, well, no, this is a polynomial, so there's no place where I'm undefined. But where am I equal to 0? Well, I'm not sure. So set 12x squared minus 36x equal to 0, and let's solve for x. Well, I notice that I can pull out a 12x because it's the greatest common factor, and I'd be left with x minus 3. Set both of those equal to 0, 12x equal to 0, and x minus 3 equal to 0. Here divide by 12, I get x is equal to 0. And here add 3, and I get x is equal to 3. So the two numbers that I get there are 0 and 3. Step 2 says put those numbers on a number line. So here's my number line, and my numbers are 0 and 3. Step 3 says choose a test value from each one of the sections. So from negative infinity to 0, I'll choose negative 1. From 0 to 3, I'll choose 1. And from 3 to positive infinity, I'll choose 4. And then we need to find the value of the second derivative at each one of those numbers, at negative 1, at 1, and at 4. So let's grab the calculator to figure that out. Okay, recall this is my second derivative. So we're going to be plugging things into that. So we're going to be plugging in the number negative 1 first. So 12 times negative 1 squared minus 36 times negative 1. And I end up with positive 48. So this is going to be a positive number. So since it's a positive number, that means that in this interval we're going to be concave up. Let's see what happens at f double prime of 1. So we'll say 12 times 1 squared minus 36 times 1, and we end up with a negative number. So this is a negative number, which means that in this interval I am concave down. And finally, let's plug in the number 4 and see what happens there. So 12 times 4 squared minus 36 times 4, and we end up with another positive number, which means that in that interval we are going to be concave up. So for writing our intervals of concavity, we know that f of x is concave up from the intervals negative infinity to 0, and again from 3 to positive infinity. And it's going to be concave down from the interval from 0 to 3. Then we need to find our points of inflection. Well, did we change concavity? We sure did. We changed concavity twice. We went from being concave up, looking like a U, to concave down, looking like an N. And then from concave down, looking like an N, to concave up, looking like a U. So we changed concavity at 0 and at 3. So to find those 2 points, first we're going to plug 0 into our original function, and then we'll plug 3 into our original function. So again, let's grab the calculator to figure that out. So 0 to the 4th minus 6 times 0 cubed plus 2 times 0 plus 8 is 8. So that's the point 0, 8. And then the other point of inflection. So what I'm going to do here is I'm just going to hit second and enter, and then go back and make all of my zeros into the number 3. So 3 to the 4th minus 6 times 3 to the 3rd plus 2 times 3 plus 8. And we end up with negative 67. So our other point of inflection is at 3 comma negative 67. So we have 2 points of inflection, one at 0, 8, and one at 3 comma negative 67. Let's do the same here for example number 4. So for example 4, again, the first thing we need to do, step 1, is find the second derivative. But in order to find the second derivative, I first need to find my first derivative. Let's find the first derivative. So the derivative of e to the 3x is e to the 3x times the derivative of 3x. Well, the derivative of 3x is 3. Minus the derivative of 9e to the x. Well, 9 is a constant multiplier. It multiplies along. And the derivative of e to the x is e to the x times the derivative of x. Well, the derivative of x is 1. So if I rewrite this, f prime of x is equal to 3e to the 3x minus 9e to the x. Then let's find the second derivative. So the second derivative, f double prime of x, well, 3 is a constant multiplier. It multiplies along. The derivative of e to the 3x is e to the 3x times 3 minus the derivative of 9e to the x is 9e to the x times 1. And then if we clean this up, we're looking at 9e to the 3x minus 9e to the x. So then we need to find our partition numbers. We need to figure out where is this second derivative equal to 0 and where is this second derivative undefined. Well, e to the x is defined everywhere. Its domain is all real numbers, so there's nowhere where it's undefined. And now let's figure out where is this thing equal to 0. So 9e to the 3x minus 9e to the x is equal to 0. And I need to solve it for x. Well, the first thing that I can do here is maybe notice that I have e to the 3x and e to the x and a 9 and a 9, so that my greatest common factor is 9e to the x, because they all have a 9e to the x in common. And if I were to factor that out, I'd end up with e to the 2x from my first term minus 1. So now if I set both of these equal to 0 to solve for x, over here on the left I have 9e to the x is equal to 0, and over here I have e to the 2x minus 1 equals 0. Well, we know that in order to solve these types of exponential equations, we have to isolate the base first. So I need to get e to the x by itself here. So first divide both sides by 9, and I get e to the x is equal to 0. If I take the natural log of both sides, the natural log of e to the x equals the natural log of 0. The calculator, right when I try to take the natural log of 0, is going to tell me error. You can't take the natural log of 0. It's not part of the domain. So from here, I don't have any place where e to the x is equal to 0. Let's look at the other one. First, I add 1 to both sides because I still need to isolate e to the 2x. So adding 1 to both sides, I get e to the 2x is equal to 1. Again, I take the natural log of both sides, so the natural log of e to the 2x is equal to the natural log of 1. Well, here natural log and e cancel, and this would just be 2x, and I take the natural log of 1, and you guys might remember this, but the natural log of 1 is equal to 0. So I get 2x is equal to 0. Divide both sides by 2, and I get x is equal to 0. So my only partition number is x is equal to 0. So then step 2 says to place that number on the number line. So again, the only number I got was 0. For step 3, we choose a test value from each one of the intervals. So from negative infinity to 0, I'll choose negative 1, and from 0 to infinity, I'll choose positive 1. And then we need to evaluate this at the second derivative and figure out if it's positive or negative. So again, grab a calculator to figure that out. Call this is my second derivative. So I'm going to say 9 times e raised to the 3 times negative 1 minus 9 times e raised to the negative 1. I hit enter and I get a negative value, which means that I am negative in this interval or concave down. Now let's figure out what happens when I have f of 1 in here. And again, what I'm going to do is I'm just going to hit second and entry, and I'm going to change my negative 1s into positive 1s. So delete, delete, hit enter, and I get a positive number. So the second derivative is positive at that value, and if it's positive, that means that in that interval I am concave up. So for us, that means that f of x is concave up from the interval from 0 to infinity, and it's going to be concave down from the interval from negative infinity to 0. Since I change concavity at 0, I know that I'm going to have an inflection point. Now the x value of my inflection point is 0. To find the y value, again, I need to plug 0 into that original function. So recall, this is my original function. So I just need to figure out what is e raised to the 3 times 0 minus 9 raised to the 0. And you end up with negative 8. So my point of inflection is at 0, negative 8. So that means that I will change concavity at the point 0, negative 8 on my graph. Let's look at something a little different. What if I give you all of this information and I ask you to graph f? So I give you all of this information and we're asked to graph f. Well, let's see what kind of information we're given, and then we'll do our best to graph the function. So first we're given f of 0 equals negative 2, f of 1 equals 0, and f of 2 equals 4. Well, all of these are just ordered pairs. So f of 0 is negative 2, f of 1 is 0, and f of 2 is 4. So those are just all ordered pairs. Then I'm given information about my first derivative. This is all my first derivative, this is all my first derivative, and this is all my first derivative. So let's graph this on a number line. Well, again, I'm told that my first derivative is equal to 0 at the value of 0 and 2, and that my first derivative is not defined at 1. So those would be my critical numbers. And I'm also told that the first derivative is greater than 0 at the interval from 0 to 1 and the interval from 1 to 2. And that my first derivative is less than 0 from the interval from negative infinity to 0 and 2 to positive infinity. Remember here again, this is going to be where f prime of 0 equals 0, where f prime of 1 is not defined, and finally here where f prime of 2 is equal to 0. So from this, what I can gather is that my graph of f here is going to be decreasing and then increasing. And if I go from decreasing to increasing, I should have a min. And then I'll be increasing to increasing some more. And I won't be defined at that point, so I probably have one of those vertical tangents at that point. So I should have a vertical tangent at the point. So we should draw that to show a vertical tangent. So at 1 we'll have a vertical tangent. And then we go from increasing to decreasing, so here we should have a min. So again, here's increasing and here is decreasing. Well, what else do I know? Well, I also am given information about my second derivative. So I know that my second derivative is not defined at 1. So if I draw a number line to represent what I have here, at the value of 1, I know that f double prime of x is not defined. I also know that the second derivative is greater than 0, so it's positive in the interval from negative infinity to 1, which means I'm concave up. And I'm negative in the interval from 1 to infinity, which means I'm concave down. So that's all the information I have. So what I typically like to do is look at this just as sections real quick. If I look at it between these sections, from negative infinity to 0, I know that I should be decreasing and concave up. Remember, concave up looks like a U, and concave down looks like an N. So in order to be decreasing and concave up, I need to look like the left side of the U. So I know that in that section, I'll be looking like the left side of the U. So coming in to this point 0, I should be looking like the left side of the U. Then in between 0 and 1, I know that I'm going to be increasing and concave up. Well, an increasing concave up looks like the right side of the U. So in that section, I know that I need to be increasing and concave up, which means I'm going to look like this. And notice I have a min just as I should at 0. Then I need to be increasing and concave down in my next section. So I'm increasing and concave down. Well, increasing and concave down looks like the left side of the N. So in that section, increasing concave down, I will look like this. Now notice I would have a vertical tangent at x equal 1. So I'll have a vertical tangent at x equal 1. I can go through and draw that just a little bit better. But notice right here at x equal 1, I would have a vertical tangent, which is perfect because I should not be defined at that point. And then finally, in the last little section here, I know that I am decreasing and concave down. Well, decreasing and concave down looks like the right side of the letter N. So I know that in that section, I'm going to look like the right side of the letter N. So from here, I'm going to be going down. And that 0.2, 4 is a maximum. I wrote minimum, but that is incorrect. This should have said maximum, because if you go from increasing to decreasing, that should have been a maximum. And notice you will have a maximum at that point. So this is the graph of f of x using all that information.